Hello everyone, I'm Shruti Kesri. I'm working as assistant professor in ABES Engineering College, Ghaziabad in Computer Science Department. Today I'm going to discuss about the Prim algorithm. In this video, I will discuss the concept of Prim algorithm and also all the steps for creating minimum spanning tree by using the Prim algorithm. And I will also discuss about an example with complexity analysis. As we all know that the Prim's algorithm is basically a greedy algorithm. When we are talking about the greedy algorithm will always consider the optimal value, or you can say nearest optimal value. It can be minimum, it can be maximum. If you want to calculate the cost, then we will go for the minimum value. If you want to calculate the profit, then we can go for the maximum value. But in case of minimum spanning tree, we are considering the minimum cost so that you can form a spanning tree which is having the minimum cost. In this algorithm, we will start with an empty spanning tree, and this is basically that maintaining two set of vertices. One set of vertices is basically containing all the vertices which are not yet to be included in the minimum spanning tree. And second set is containing all the vertices which are the part of your spanning tree. And after initializing these two sets, at each and every step, you will consider all the edges and fix the minimum weight edge. Because I'm again, as I already told that this is a greedy algorithm, it will go for the minimum value. So it will consider only that edge which is giving you the minimum edge. And after picking the edge, it will move the other endpoint of the edge to the set containing minimum spanning tree. For creating the minimum spanning tree, just we are going for the some steps. First, you need to assign key values to all the vertices in the graph and initialize this key value as infinity. Infinity, if we are going for any minimum value, always consider the positive infinity value so that we can easily check that given value is less than or not. If we are going for the maximum value, always go for the minimum value, that is the minus infinity, so that you can easily check the maximum value. So in this algorithm, we are going for the minimum value. That's why we are initializing the key value as the positive infinity, which is the highest value. And after that, we need to consider which one is the first vertex. And after that, we will reinitialize the key value of the first vertex as 0. Then after considering all these things, after initializing all these things, we need to perform this loop of the task for each and every vertices until and unless that vertices is included in the set of minimum spanning tree. Now pick vertex U, which is not in the MST set and has minimum key value. Include this U to the MST set, and after including that thing, you need to check all the adjacent vertices of U. And again, you need to check that if that particular adjacent vertex is not the part of your MST set and is having the less key value, is having the less value at the edge as compared to the key value, then update this one. We will understand this one by using this pseudocode. In this pseudocode, I am passing three parameters here. First is G. G is giving the complete graph. W is passing the weight of the graph. And R is initially defining the vertex, start vertex, from where you will start the drawing of minimum spanning tree. Here, for each and every vertex of your graph, you are initializing the key value as infinity, as I already discussed about this one. And then pi of u. Pi is basically a set which will contain all the vertex which are already included in MST. So you can say pi will having all the vertex which is the part of your MST. And after initializing these things, by using the value of r, that is your start vertex, update the value of key value of r as 0. Now assign all the vertex to the queue. As already discussed that we will maintain two sets. First is for all the vertices which are the part of your MST, and second is which is not yet to be included. So here Q is the set which is containing all the vertex which is yet to be included in the MST. and then we will start a loop until q is not equals to 5, until q is empty. So first you need to extract the minimum key value. As already discussed that, you can see that all the key values are defined as infinity. Only the key value of your start vertex is updated as 0. So it will extract the minimum key value, that is your start vertex. And you need to check all the vertices which are adjacent to the U, and for all the edges, you need to consider these two conditions. First, V should be the element of your Q. It means this is yet to be included in the MST, and the weight of the edge from U to V is less than the existing key value of your V. Only if these two conditions are true, then you need to update pi V. Pi is containing the parent of your V. It means to say that suppose you have two vertices, that is U and V, and you are considering the edge from U to V, then U will consider as the parent of your V. So you need to update that thing in the pi set, and again update the key value of V by the edge weight of U to V. We can understand these things by considering an example. Here I am taking an example in which you need to construct a minimum spanning tree by using the Prim's algorithm. So according to the algorithm, I have initialized these three things. First, your vertices and the key values initialized at the infinity of each and every vertex, and put the value of pi as nil, and this Q is containing all the vertices which are yet to be included in the vertices. Now we are passing that, suppose small a is the start vertex, then the key value of the small a will become 0. Now according to the algorithm, here you need to extract the minimum value of your set. A is containing the minimum value as 0, and all the other vertices are containing the value as infinity. So we are extracting this one and remove this value from the Q. Now again check for each the adjacent of the U. For given graph, the adjacent vertex of A is B and H. Now consider all the condition. B is the part of your capital Q, yes, and weight of U to V, weight of A to B is 4, and the existing key value of V is infinity. Both conditions are true. That is, 4 is less than infinity and V is the element of your Q. Then you need to update that thing. That is, update the pi value of V as A and the key value of V as 4. Similarly, for the H, H is the element of capital Q, and the weight of H from A to H is 8, and the existing weight of H is infinity. So 8 is less than infinity, then you can consider this condition. Now update the pi value of H as A and update the key value of H as 8 in place of infinity. Again, this loop will get moved to the do you extract min q, and then choose the minimum value. Here 4 and 8 and all others are infinity. So you will choose that 4. Now we're considering B, and B will get removed from the Q also. Now check that thing, the adjacent of the B. If you are considering adjacent of the B, then in that case there are two vertex again. First is your C and second is your H. Now again check the condition about this one. C is also part of your capital Q, and the weight of your edge from B to C is 8. Existing value of C is infinity. So condition are true. Update this value as parent of C will become B and the key value will become 8. Now we'll consider again about the H. H is the part of your capital Q, and the weight of B to H is 11, and the existing weight of H is 8. This condition is not true, so no need to update this. Now again we will check about this one. In the rest remaining the vertices of this one, which one is having the minimum value? Here C and H is having the same key value, so you can choose any one. Just suppose we are choosing the C value, C vertex, remove this vertex from the H and consider all the adjacent vertices of the C. Here C is containing three vertices, that is D, I and B and F. Now we'll consider about this one. D is the element of your Q, right? And the edge weight of C to D is 7 and the existing weight of the D is infinity. So 7 is less than infinity, condition is true. Then update the value of pi as C and update the weight as 7. Now we'll consider about the I. C to I weight edge is containing the weight of 2 and the current weight of key value of I is infinity. 2 is less than infinity and I is the part of a capital Q. Both conditions are true. So you need to update this one. Update the parent of I as C and update the key value of I as 2. Now consider B. B is not the part of your capital Q. So we will not consider this one. Again, check for the F. F is the part of your capital Q and the weight of the H from C to F is 4 and the current key value is infinity. Both conditions are true. So update the value of C, update the value of parent of F is as C and the key value as 4. Again, check the rest vertices which is having the less weight, that is I is containing 2 weight. So we'll consider I as next element and then remove I from the Q and check the adjacent of I, that is C, H and G. C is not the part of your capital Q. It's already added in the MST, so we will not consider this one. Now we will check for the H. The edge weight of I to H is 7 and the current weight of H is 8. 7 is less than 8. The condition is true. So you can update this one. Update the parent of H is as I and the weight is 7. Now for the G value, weight of the I to G is 6 and the current weight key value of the G is infinity. So 6 is less than infinity and G is a part of your capital Q. Then you will consider that this condition is true. Update this value. The parent of G will become I and the key value will become 6. Now again, we will check the rest vertices which is having the less value. That is your F. F is containing the 4 value. We will consider this F here. Now check the all the edges, all the vertices which are adjacent to the F. Now F is containing C, D, E and G. 4 vertices are adjacent to the C. Then C is not part of your Q. We will not consider this one. We will check for the D. D is the part of your Q and the edge weight from the F to D is 40 and the current weight of D is 7. So condition is not true. We will not change for this one. We will check for the E again. Now the weight of the edge from F to E is 10 and the current weight of E is infinity and E is the part of your capital Q. Both conditions are true. Update this one, that is parent of F and parent of E will become F and the weight will become 10. Now we will check for the G. G is the part of your capital Q and the edge weight from F to G is 2 and the current weight of F is 6. Both conditions are true. Then update this one. The parent will become F and the weight will become 2. Now we will check again. D, E, G, H. D, E, G, H. G is containing the minimum value. So we will check. We will choose this one as an key and check the adjacent of your G. Now remove this one from Q and check the adjacent of G, that is I, H and F. As already knew that F is not part of your capital Q, I is also not part of your capital Q, H is the part of this one. So you need to check that H weight of the G to H is 1 and the current weight of H is 7. Both condition are true. Update this one, that is the parent of H will become G and the weight will become 1. Now check this one, H is containing the minimum value. We will traverse this one. The adjacent of H is A, B, I, and G. A is not part of your capital Q, B is not part of your capital Q, I is not part of your capital Q, G is not part of your capital Q. So it will not change any value. Now we'll consider D and E. D is containing the weight 7 and E is containing the weight 10. So minimum value is D. We will consider D here and then we'll check the adjacent vertex of D. Adjacent vertices of D are C, E, and F. C is not part of your capital Q, E is also not part of your capital Q, and F is also not part of your capital Q. Sorry, E is the part of your capital Q. Then check the weight of this one. D to E, it's containing 9 weight, and the current key value of E is 10. Condition is true. Update this one. Parent of E will become D and the weight will become 9. Now the last vertex, that is E. No need to check another one because this will not consider anything here. Now this will become your final. E is containing all the edges which we are adding in MST. Pi is defining which edge we will consider. Like this one, you need to consider B to A, C to B, D to C, E to D, and F to C, and G to F, and H to G, and I to C. Now, this will give you the exact cost of your MST. You need to add this one. This one, 37 will be the cost of your minimum spanning tree. Now, about the complexity analysis of this algorithm, as I've divided this algorithm in two parts. First part, this is defining just the initialization part. So you need to initialize the key value of each and every vertex. So you need to traverse this value by the O of V. And for updating the key value of your start vertex, this will cost us O of 1. Now, about the second part, when we are considering the while loop until and unless that Q is empty. So you need to extract the minimum value. For extracting the minimum value, this will become, because you need to create a heap. And when you are creating a heap, you need to use the complexity of that is O of E. And then for extracting the value, you are extracting each and every vertex time. For extracting the value, you need to consider complexity of log V, but you are extracting the value how many times? That is V times. So total complete complexity of that extracting the minimum part is V log V. And then if that graph is your sparse graph, then decreasing the key value will cost only O of 1 cost. But you're decreasing the cost for each and every edge. You're checking for that value for each and every edge, and it will become O of E. So after combining all the complexity at the steps, you will get that for the sparse graph, that complexity is O of E plus V log V. But when we are considering the dense graph, that decreasing of key, because that edges will be increased. So in that case, the complexity will increase and the total decrease key cost will become O of V square. So it will also reflect the overall complexity of the algorithm and it will become O of V square. That's all. And these are the references which I go through for this video.